Okay, so we've played with a few examples of finding eigenvalues and eigenvectors for a 2x2 matrix. Now we'd like to describe just a general method for doing that for any matrix. We are looking at page 93 here. Okay, we're just going to run through the steps. Okay, these are going to be the same steps that you learned when you discussed this topic in Math 241. Okay, so first, in this process of finding eigenvalues and eigenvectors, we're going to start by taking the determinant of our matrix A minus lambda I and setting it equal to 0. Okay, that's the same process. Okay, that we talked about before. Let me see if I can write that a little bit more neatly here. And what's interesting about that equation, you've seen this in the calculations that we've already done, is that we get a polynomial in lambda. Okay, something that we can generally factor in order to find our eigenvalues. There's a name for this polynomial. It's called the characteristic polynomial of our matrix. Okay, and so if A is an n by n matrix, then that means that this polynomial can have at most n roots. Okay, which is another way of saying that a matrix can have at most n eigenvalues, can't be bigger than the size of the matrix, essentially. Okay, so step 1 tells us what our eigenvalues are, and then we move on to step 2 to find our eigenvectors, which involves just solving a system of equations one at a time for each eigenvalue. Okay, so you would take one of your eigenvalues, form the system A minus lambda I times v equals 0, and you would just solve that. Okay, using the standard method that we've talked about for solving equations. Okay, and you're going to have free variables. The question is how many you have. Okay, so if you have k of them, let's say, that just means that there are k linearly independent eigenvalues that can be found. Okay, and kind of an algorithm for finding those, we'll see this in the example that we do in a minute here, is to just choose a non-zero value for each free variable one at a time and let all of the other free variables be 0. That's the quickest way to kind of lay your hands on k linearly independent eigenvectors. Okay, and just a word about terminology down here at the bottom, this note. Okay, so if lambda is an eigenvalue, then there's a name for the set of solutions to that system that we just wrote down above. Okay, it's called the eigenspace associated with the eigenvalue. We used that terminology a minute ago one time. Okay, and so we can make one more comment here. If an eigenvalue is repeated k times, then the associated eigenspace can have a dimension of at most k. That turns out to be a fact, which we